So am I audible?
Yes. Audible to you. Yes, let me start. Basic introduce yourself.
Sir, yes. I'm Vishnu Shah. I did my schooling 10th and 12th from Shantipur Municipal High School with 93.7 and 88% respectively. Then I completed my BSc in Chemistry Honors from University of Kalyani with 88 percentile. Also, I then qualified the IIT-JAM examinations result in rank 126 and got admitted into the Indian Institute of Science, Bangalore. Then I completed my master's from there. Apart from that, I qualified CS and AGRF with rank 22 and also the GATE 2023 154 rank.
Yes, good. Today topic is coordination chemistry. Yes, I'm right.
Yes, sir. Yes, sir.
Yeah, let me start. Basic introduce of coordination chemistry. What is coordination chemistry? What are the main application of coordination chemistry?
Coordination chemistry is generally there is a bond between the metal and the ligand within the sphere with a particular stoichiometric ratio, and this can be tuned. The main applications of the stoichiometry, applications of that, it can be used in different field using like the cisplatin synthesis, the transplantation, which are the carcinogenic examinations, other as that is complexes and use and the spinotronics recently, like photo switchable materials, because some complexes when irradiated with the light it shows pin change and their color also changed. That's
Yes, what is coordination compound?
coordination compound is that within the in a compound in which there is a direct coordinate bond between the metal and the ligand, some defined ligand, and we can tune that ligand to we can use defined ligand within the coordination spheres.
What the example of coordination compound? Any example?
Yes, sir. This is the one example, sir, right? So this is the one coordination chemistry compound. Chromium.
Yes, sir. Explain one by one.
Okay, here is the chromium is the metal and H2 is present within the coordination sphere. So this is called the so this is directly bonded to the chromium. Now 3 plus is the valency. This is called the primary coordination number, and secondary coordination number is the 6, where because the 6 ligands surrounding the ligand is surrounding the chromium around it. So this is the cell. Yeah. And the chlorine minus ion supposed to be considered to satisfy the translator is called a counter.
Yes, what is Werner theory? What are main application of Werner theory in coordination?
The one theory generally tells us about the stability of the compound using the wear. Like it is totally bent of the valence bond theory, where it is formed that there is a formations of the hybridizations of the metal orbital, overlap of the hybridized metal orbital with the ligand. Like if you consider this chromium 3, here is a 3d electron and here's a 2 vacant d electron. So the it is generally the vacant it has generally the D2sp3 configurations filled by the ligand, like the 2d S and P3. These three orbital is generally filled by the ligand orbital. So this is the general idea. So here the ligand orbital under overlap with the T2sp3 configurations. So this is the covalent bond is forming between them. through the hybridization. This is the one of the one theory.
Yes. What the difference between primary and secondary valencies? What the example?
So here the complex that I have written. So here the chromium H2 whole 6 Cl3. The Cl3 is present outside. The primary coordination is nothing but the oxidation state, that is the 3 plus, and the secondary valence is the 6 higher H2 molecule, that is the joined to the, that is a coordination number.
Yes. What the limitation of Werner theory?
The Warner theory actually doesn't tell about their origin of their color, along with it's only able to distinguish that a magnetism is like SD2 SP3 or SP3 configuration about the structure, but it didn't give any idea about the color. There are UV absorption spectroscopy on these things.
Yes, good. What is ligands? Now, how many types of ligands in coordination? Explain one by one.
Ligands means in the coordination chemistry, different type of generally, according to the Warner theory, the ligands are the Lewis bases who can donate the electron to the metal to the coordinate bond, coordination bond. So and it's around the metal to give a particular geometry like octahedral, tetrahedral. So the ligand is different type based on the density, flexibility. There is some co-ligand who can donate their electron. Both some of them is called ambidentate ligand. Flexidentate ligand is a ligand which can make their density flexible, like SO3 2 minus, NO3 minus. These are flexidentate ligand. And yeah, so this is the ligand may be always either neutral or negative. Neutral ligand is the CO and H2O, all these things. And negative ligand is like OH minus S3 minus, but it can't be positive because it's accidentally based. So it should have some different. So,
What is wide-ended ligands? What the example of wide-ended?
one of the bidentate ligand is the ethylene diamine, sir.
What the uses of wide-ended ligands in coordination? The main function.
Bipyridine also, sir, possible bipyridine. So it's generally used in the formation of optically pure complex. Like if we add the three ligand like chromium bipyridine whole 3 plus, so it has a structure which is optically active, and we got two structure. One is the its main enantiomer, and the one outside just join.
Yes. What is hexadentate ligand? What the example of hexadentate ligands in coordination?
Exactly, it's the ethylene EDTA, sir. 10 diamine tetracetic acid, sir.
What the main function of EDTA in coordination?
EDTA generally used to chelate some poisonous species, generally PB2 plus, community plus. If we take in the human, if we take some poisonous things, so if we then it was used to make the chelate compounds so that we can get rid of this poisonous thing, poisonous metal like PB2 plus.
What is bridging ligand and how many types of bridging ligands?
So bridging ligands, it's a ligand which generally bridge between two ligand. It generally define. I am just pyrazine is the one of the example of the bridging ligand, sir. Pyrazine. Also, hydroxy group also can make bridging oxygen bridging ligand, sir.
What the difference between negative, positive, and neutral ligands? What the examples?
Yes, sir. This is the one of the examples, sir. Bridging ligand, this one, sir. Like here, the hydroxy base is present as a bridging
Yes.
ligand.
Yes, bridging ligands. Yes, copper, chlorine. Yes.
Yes.
Yeah. Next one. What the difference between negative, positive, and neutral ligands?
Negative positive ligand generally is not possible, can't be. But sometimes NO is generally as per the 3 plus. So this is one example, like NO plus only the positive ligand in the linear form. And the neutral ligand is acts as a sigma donor, that is the H2O, NH3, ammonia, these things. And the negative is the sigma donor and pi donor, like hydroxo, nitrite, all this ligand set.
Yes. Any limitation of ligands?
Any limitations are there is actually no limitations
Yes.
because this is for this reason this stream was developed, sir.
Yes. What's the difference between symmetrical and unsymmetrical bidentate ligand?
Yeah, symmetrical bidentate ligand generally occur like CN and PN. I am just writing, sir. There's a triethylene diamine and a 1,2 propylene diamine. So this is the symmetrical ligand that I'm sorry. The TN, triethylene diamine is the
Yes.
symmetrical ligand, and trimethylene 1,2 diamine is the ligand.
Yes. Yes. Right. Next one. What is macrocyclic ligands?
Macrocyclic ligands, it's generally porphyrin you can consider one of the macrocyclic ligands where the more than 2 or 3 donor atom is there and their cycle. Then all the ligands in the plane are connected through cycle. One of the example is the porphyrin, the hemoglobin cell. It's a macrocyclic ligand.
Yes. Good. One topic is clear. Next topic is coordination is isomerase. What is isomerase? Now, how many types of isomerase?
Isomerism is generally the geometrical or optical. So the geometrical isomerism is further classified into the hydrate isomerism, then linkage isomerism, then coordination, position isomerism is also there. So and polymerization isomerism.
First of all, isomerase is a two types: structural
Yes, it's
isomerase and stereoisomerase. Yes,
yes, a structure
stereo,
geometrical and
yes,
stereoisomerism.
stereoisomerase is two types: geometrical and optical. And structural isomerase is seven types: ionization, hydrate,
Yes,
linkage, coordination, positive ligand, polymerization.
yes, this.
Yes, what is the difference
Yes.
between organic isomerase and inorganic isomerase? What is the difference?
Difference between inorganic and organic isomerism. Yeah, sir. In the organic isomerism, generally one atom is sufficient to do center called asymmetric center. Suppose I'm drawing cell one example through which I can. In the organic isomerism, generally carbon, the ligands are generally joined to the carbon, but in the coordination isomerism, it's generally joined to the metal. This is the basic difference first. And generally, most of the time, it was depend on the coordination in the coordination chemistry, like 4, 6. But only single atom can show the asymmetric center. Like if the four ligands are different in the carbon atom, it can show isomerism in the organic isomerism, sir.
Yes. Stereoisomerism is present in organic chemistry. Then the types of conformation and configuration is a carbon.
Yes, yes, sir.
Non-stereomerium, diastereomerium. This depend on only carbon compounds. Yes, no?
Only carbon compound and the ligand and the atoms are bonded to a atom, sir.
Yes.
But here it is depends on the ligand, sir.
Yes. Right. Right answer. Yes. Good. What's the difference between geometrical and optical isomerism?
In the geometrical isomerism, it is generally occur in for the different arrangement of the ligand, either cis or trans. This may be the geometrical, and optical isomerism occur due to the optical chirality. That is, if it gives two non-superimposable, yes, a non-superimposable mirror image or not. So based on that, we can, yes, if we consider the cis compound, one cis compound and a trans compound, these are example of two geometrical isomerism. But the cis compound is only the optically active because it can give it. So I'm just writing, sir. So this is the cis and trans compound here. So the cis compound is optically active because it can give its mirror image, but trans there is a sigma planar symmetry, so that's why it's optically inactive, sir.
Yes. Right. Optically active. You talk about optically active, inactive. What's the difference between optically active and active? Complex.
Optical activity generally related to it's better generally related to how if we generally optical spectrometer, if we put our compound, if it rotate either clockwise and anti-clockwise directions, that is it's called a dextro-rotatory and levo-rotatory. So based on that, this optical activity can be measured. How it is generally the how it is rotating the light, plane polarized lights.
Yes. What is linkage isomerism?
Linkage isomerism because of the ambident cell ligand. Like NCS, I'm just writing. We consider this complex NCS, and if we consider some other complex like CO, if H2, whole 5, SCL. So here the cobalt is bonding to the nitrogen, so it's a heart center. So here the nitrogen is bonding to the NCS ligand, and if in the other complex oxygen cobalt is a soft center, so it is bonded to the sulfur. So this is the linkage isomerisms.
हाँ थोड़ा मॉक ले रहा हूँ अभी अभी 20 मिनट बाद ठीक है यस यस कैरी ऑन
So in this compound, this is the compound. Then cobalt is joined to the nitrogen. If it is a hard center, like ammonia is present, and if you consider the H2, it's a soft center, so it's joined to the sulfur. So this is the one instance, like because of the ambident ligands.
यस Yes, what is the difference between facial and meridional isomers? What is the difference?
Axial isomer generally where the three atom occupy the one face and the meridional it is generally occur at the plane with the octahedral complex. So this is the facial isomer and this is the meridional isomer.
Yes.
This one is the facial, this one is meridional isomer.
What is chility ligands? Chility complex in isomerase.
Dating ligand is formed by the cyclic if the bidentate or tridentate ligand is present within the complex. This is a chelating ligand. The types are shown. This one.
Any limitation of isomerase?
Generally, limitation there is no limitation, but sometimes it was found that the one isomer like cis optically have some applications in the biology or transfer some applications. So they are based on the geometry and the entire occurrence of the ligand identity. It is generally property changes, both the physical and the like. Cis has a greater dipole moment, trans has a greater dipole moment. So because of that, the cis shows higher boiling point compared to the trans ones.
Yes. Good. Next, move on. Next topic is IPSC nomenclature in coordination chemistry. What is IPSC nomenclature? What is the main application of IPSC in chemistry? Explain.
Yeah, this is the one nomenclature to IPHC. It's a nomenclature to identify one compound through its one of the name, and it is generally used to naming of the compound like first because it can like the amine ligand name, then followed by the metal name, and also all this what primary valence and secondary valence is generally shown into one line through one name.
Yes. What is the name of natural neutral ligands in according to IPSC nomenclature?
This carbonyl, all these things are can be done. So like nitrosyl, these are the neutral ligand. Like amine, the NH3 is called as amine, histo called as qua, cyanoid called as cyanoid. So all these things.
Yes. Amine, carbonyls, aqua, nitrosyls, dinitrogen, dioxygen. Yes, so many.
Dioxygens are also, yeah, dinitrogen.
Yes. EPS3, PCl3.
Hmm.
The next,
Previous is called phosphines, sir.
yes,
Diphenyl phosphine or phosphines.
yes. Diphenyl phosphine, yes. Urea also.
Yes, urea is just called as urea.
Yes, next move on. Theories in coordination. First of all, what is valence band theory? What is the main application of valence band theory in coordination? Explain.
Valence bond theory generally first theory in the year that generally help us to first interpret the structure of the quaternation compound indeed. Some of the main postulates of it that the metal there is a hybridization take place between the metal orbital and the ligand orbital, and this then the ligand orbital binds from the either low spin complex and the high spin complex dependent on the strength of the ligand on the spectrochemical series. And this is the one of the example that I can show is that so this one. So here is the chromium H2O2 6. So here have to consider the chromium 3 plus. So the three orbital there is three electron and if some strong spin ligand like ammonia is approaching. So it has a D2, it's from the D2sp3 hybridization. This D2sp3 hybridization orbital of the hybridized orbital of the metal undergo hybridization with the ligand and these are filled by the ligand electron to form the D2sp3. Similarly, outer sphere complex like sp3d2 also possible, sir.
Yes, what the limitation of valence bond theory?
Valence bond theory generally give only the idea about the geometry, but can't able to explain their magnetic what is the basis of the spectrochemical series, like how what from where the color is originating, how the complex is stabilized, or what is the factor to stabilize this theory. These are not known, sir. This is the main disadvantage, sir. Theory.
Yes. Valence bond theories can't explain the color and electronic spectra of complex. Yes, no.
Yes, sir. Color and electron spectra. It can't explain, sir.
It can't explain the rate of and reactions and mechanism of reactions of complexes.
Yes,
Reactions.
sir. Outer sphere, either outer sphere or the inner sphere reaction is gone going or not. This can't also be, sir, explained from this correlation theory. That can be explained to the disruptive theory based on
Yes,
the
it,
CFSC, sir.
it can't explain the distortion in some octahedral complex.
Yes, sir. John Taylor distortion also can't explain, sir.
Yes. It can't explain the nature of ligands, which ligands is stronger
Yes,
and
the basis for the spectrochemical series, sir. Yes,
yeah.
sir.
Yes, good. Next, move on. Next theory is CFT, crystal field theory. What the main application of crystal field theory? Explain briefly.
The main application of the crystal field theory, the drawback to overcome the drawback of the valence bond theory, and the main postulates of that, the ligands and the metal is considered as a point charge. The ligand is considered the negative charge and the it is considered positive charge, and there is a Coulombic force of attraction. Completely ionic interactions is there between the ligand. So when the ligand is in the spherical form, like when there is all the ligand presence in the all directions, there is no splitting of the d orbital that is there in the degenerate state. But if we go to the different, but when the ligand approaches along the different axes, in suppose the octahedral, tetrahedral, and other geometry, then there is a splitting of the orbital. Some get stabilized, some of the orbital get destabilized by the equal amount of energies. So this is the basis of the C-sharp splitting and CFC theory, sir. Safety.
What is spectrochemical series?
Yeah, the spectrochemical series based on the experimental is generally called the strength of them. Generally, it's a series which generally gives the strength of the ligand, like NO plus U, CN minus, a strong field ligand present at the right side, weak field ligand are present on the left side, moderate at the borderline of the middle side, like NO plus U, CN minus, then fluorine, chlorine, bromine, that is left side and the that are the weak field ligands are, and some in the bottom line H2 ammonia, Sc and all these things are the ligands are things.
Yes, what is the magnitude of tetrahedral octahedral sp complex and what is the magnitude?
Generally, the delta O equals to 8 by 9 into delta 3. Like delta octahedral, this is the same.
Tetrahedral
8 by
octahedral.
yes, sir. 4 by 9 into delta T. So this one, sir, this is the relationship between the tetroctet and the tetrad.
Yes. 4 by 9 in tetrahedral, 8 by 9.
Delta octahedral equals to 4 by 9 into delta tetrad.
Yes. Which factor is affecting by magnitude?
Generally, then the tetrahedral, the ligands are the 4, and but in the octahedral, it is 6. So this is the ligand in tetrahedral is a 2/3 of the octahedral. So that's why 2/3 contribution. Another 2/3 contribution is coming because in the tetrahedral geometry, no ligand is approaching directly to the ligand. So that's why their sideways approach is present. So that from that another 2 by 3 contribution is coming. So 2 by 3 into 2 by 3 equals to 4 9. Sir.
What is CFSC? What the main application of crystal field is splitting energy?
ABS is generally used in the color, magnetism, and the stability of the complexes. All these things can be, I mean, the reaction mechanisms. These are the explained, but the stability, no, why, but still it failed in the covalent because it didn't consider the covalency, which was further it, but it can't say why this ligand is a strong field, why this ligand is a negative position, low field. So this cannot be possible to explain from the crystal field theory, sir.
What is pairing energy? What the main application of pairing energy in coordination?
So in the pairing energy, generally is present in the low spin complex. If the pairing energy is less, then a low spin complex is favored. If pairing energy is high, then the high spin complex is severely favored. And this is one type of destabilizing energy. And if the pairing energy is equal to the center self-stabilized splitting energy, then it shows equilibrium. So spin crossover both the high spin and low spin.
What is John Taylor distortion? JTD. The main application of John Taylor distortion.
Yes, sir. John Taylor distortion, sir.
Yes.
According to John Taylor distortions, any non-linear molecule undergo distortions to remove its electrical degeneracy to form the complex of more stable complex and lower symmetry. So this is the basics of the John Taylor distortions.
What the difference between static and dynamic John Taylor distortion? What the main application of this one?
In the generally the John Taylor distortions take place either at the two-way, either Z out or the Z in. If these distortions are taking place at simultaneously, it is called a dynamic John Taylor distortion, but it is occurring in the static way. This is called a static John Taylor distortion. And yeah, generally the compound which is higher splitting, like you can so for them asymmetric filling of the orbital in the EG orbital take place like D9, D6. These are also in the higher like static general distortions where there is asymmetric filling of the electron in the EG orbital, T2G orbital like D1, D2, low spin D5. These are all showing the titanium H2O, then vanadium H2O6. These are all the compound that show the dynamic general distortions. For the energy is sufficient to equalize both the Z out and Z in, elongation and the compression. So
What is spinels and how many types of spinels?
spinals generally two type. One is the three types generally. One is the normal spinal, one is the inverse spinal, another would be the random inverter spinal, like in the borderline between two.
What the main application of spinal in coordination? What the main purpose?
Spinal generally has some unique geometry that can be explained from the CPC. So I don't know what is the application in our day-to-day daily life. Spinal, I'll see. So,
Yes, three terms used in GNTD: regular octahedral, tetragonal compression, and tetragonal elongation. What the difference of these one?
yes, I'm drawing.
Yes.
So this is the tetragonal elongation form. This one, sir, is going the splitting, like what the bond along the Z axis here. So this is the Z out type general distances or the elongations, and this one is the Z in or the compressions, but the axial bonds are compressed. So,
Yes, good. Yes, good. Yes, left fast. Left part is we will discuss in next day. Yes.
yes, sir. Yes, sir.
Yes, coordination chemistry.
Okay. Shall I leave now, sir?
Yes, yes. Some second is automatically leave there.
Okay.